Okay, welcome to Lesson 18. We're going to talk about normal distributions. Specifically, we're going to talk about our favorite normal distribution. We have one that we call the standard normal distribution, and honestly, we play favorites. It's our favorite. So the idea behind standardizing is not everything's on the same scale, so it's really hard to compare things directly sometimes. So if we standardize, we can get them to both be on the same scale. So we have Sepeda took a test where they went ahead and they calculated an IQ score, whatever IQs actually measure, and they get 120 is their score. And they applied it at 2 colleges, and they, for some reason, collect student IQs of these 2 colleges, and they're normally distributed at both colleges. So given the distributions have different centers and spreads, they want to figure out like at what college did they score higher, right? So they still scored 120 at both, but is 120 higher for college 1 than it is college 2 or vice versa? That's what they want to figure out. So for anything that we have that is has a normal distribution, we can calculate what's called a z-score. So a z-score, it represents how many standard deviations away from the mean. So if you have a positive score, it means how many standard deviations above the mean. If you have a negative score, how many standard deviations below. So x is whatever the score is, minus the average at that college or whatever variable you're looking at, then divided by the standard deviation. So here, the standard normal distribution, this is a distribution that has a mean of 0 and a standard deviation of 1. So anytime we have a normal distribution, we can translate the problem we have into this normal 0, 1 distribution. And we do that because we have a table with the probabilities for the normal 0, 1 distribution. So translating it's really useful. So z, when you take your score minus the mean divided by the standard deviation, it comes out to be the number of standard deviations that an observation is from the distribution's mean. Positive means it's however many standard deviations above. Below means lower than average. So we're going to apply this idea to the IQ question. So if we're going to need this information here, so college 1 has a mean of 114 and a standard deviation of 12. College 2 has a mean of 117 and standard deviation of 10. So they're centered slightly differently from each other, and they're shaped a little differently as well. College 2 is a tiny bit narrower. So I'm going to calculate the z-scores for both colleges. And the idea is whatever college they have a higher z-score at, that means that they did higher than the average at that college. So college 1, I'm going to say, okay, I'm going to call this z1. So this is my z-score for college 1. So x minus mu over sigma of x. X is just IQ score. 120 is what they scored, minus the average at college 1 is 114, over the standard deviation at college 1. So I end up getting 6 over 12. I end up getting, and I'm going to mark this positive 0.5. So that means they are half of a standard deviation above average at college 1 as far as their IQ score. So for college 2, I'm going to use z2. So it's going to be the same setup, x minus mu over sigma, except I'm going to use the mean and standard deviation from college 2. So it's still 120 minus the average at college 2 is 117 over the standard deviation from college 2, which is 10. I end up getting 3/10. So 0.3, and I'm going to put a positive there. So at College 1, they're half as a standard deviation above average. At College 2, they're 0.3 standard deviation. So they're not quite as high above the average at College 2. So at College 1, they have a higher z-score. So the higher the z-score, the higher relative to everyone else your score was. So the idea behind standardizing is, well, there are steps here. So you start off with a normal distribution. It's centered somewhere. We're just going to call it mu. When you do this step where you subtract mu, you force it now, instead of being centered on mu, now everything's centered on 0. Then when you divide by sigma, this now makes it, oh, well, number of standard deviations away. Instead of, because for this last problem, it could have been 10 or 12 for each of these, and it's really hard. It's going to change from place to place. So we like to use this distribution, the standard normal, the normal 0, 1, as a reference distribution. So when we talk about the z-table, we have a table for this specific normal distribution. And we like to use that table to find probabilities with. It's a way for us to translate into any normal distribution can be translated into this normal 0, 1, and we can find probabilities that way. So just a comment on positive and negative. So if you get a z-score of 0, that means that if we're talking about IQs, that your IQ is exactly the middle. That's exactly the average. If you get a z-score of positive 1, that means, hey, I was, 1 standard deviation above average. So that you had a higher than average. The further this way you get, the higher than average you get. Similar this way, but with negative. So if I got a z-score of -1, that means, oh, I'm a standard deviation below the average. 2 standard deviations below the average. So the bigger that number gets in the negative direction, the lower than average, more lower than average you get. So standard normal table, finding areas. So this is we're gonna practice a little bit using the table here. So suppose I want to find the proportion of observations below a z-score of positive 0.81. So for me, if I say, okay, well, z is equal to 0.81, the first thing I like to note is this table gives me the area less than by default. So that's important to know, because if you ever want the probability higher than, you're going to have to subtract from 1. So here I have this 0.81. So I'm going to break it off into 0.08, well, yeah, and 0.01. The idea is if I combine them, I would get back to 0.081. That's the idea. So this part tells me which row to use. So I'm going to go for 0.8. And this tells me which column to use. So 0.01. So then I'm going to line up here. And I'm going to get, so probability that z is less than 0.81, that's equal to 0.7910. So honestly, this picture would actually be more like this. And we're going to continue practicing it. So back to that problem with Sepida's IQ, we can use that z-score of 0.5 and find the area under there. So it would tell me what percent of students at that college or applicants at that college scored lower than SEPTA. That's the idea. So remember, College 1, we got a z-score of 0.5. 0.5, I like to add the 0. I can break that into positive 0.5, and important that it's positive, and 0.00. Right? You can always add zeros to the end. So this is going to tell me which row, 0.5. This will tell me which column. So the probability that z is less than 0.5 is about 0.6915. So this implies that at College 1, about 69.15% of the applicants at College 1 had a lower IQ than SEPTA did. So now, suppose I might want to find greater than 0.5. So things to know, so if this is 0.5, and we already determined, looking here, that this was 0.6915, this white wedge is what we want, right? We want to know greater than 0.5. We know that area under the entire thing is 1. So we can say, well, 1 minus 0.6915. So this is going to be like 1 minus the probability that it's less than that 0.5. It's 1 minus. So I'm using that complement rule, throwback to last week. 0.6915. I'm going to get something like 0.3085. Definitely check me on that. When I talk like that, I'm usually doing the math in my head. So in essence, what we said, hey, if 69.15% of the other applicants are less than SEPTA's IQ at College 1, that means 30.85% are above. So just negative versus positive scores. I think I mentioned this already. If you get a z-score of 0, that means exactly on average. So a z-score of 0 means you didn't go above, you didn't go below average. Positive means above average. The higher the number, the more above average. The lower the number, so negative, the lower, like the more low than average. So in general, I mean, if you get a z-score of 0, that means you're average. If you're talking about exam scores, you probably don't want to be there. But there are other things where it would be good to get like a z-score of 0. Versus if you were talking about exam scores, you might want to go more on the high end. Chances are you don't want to go on the low end. But if you're talking about racing times and being faster, you might want to. So we're just going to practice using the z-table a little bit. You might notice that this is a very, very cropped version of the z-table. The z-table, it's one page front and back, or 2 pages, single-sided. I cropped it so it would be useful here. So if I want to find the probability that z is less than, I'm just going to write over here. So negative 2.57. So I want to find this shaded blue area because I want less than. So my first step, I'm going to break this up. So negative 2.5 and 0.07. And the idea, if I combine them back together, I'll get negative 2.57. So this will tell me which row. So negative 2.5. This will tell me which column. Where they line up is what I want. So 0.0051. So this is saying that, hey, this is about 0.51%. It's very low, about half of 1%, roughly. are below this value. So find the probability that we have a z greater than positive 0.62. It is, I've been noting whether it's positive or negative because it tells me which z table to look at. There's a negative z table and a positive one. So I find that useful. So I'm going to break this up again. So I can break this into positive 0.6 and 0.02. So positive 0.62. So this tells me my row. This tells me my column. So 0.7324. But now we need to double check, did I answer the question? So here, I want greater than. I actually want this white area, this white tail area. So this is going to be the same as 1 minus probability that z is less than at 0.602. So 1 minus that 0.7324. So I'm going to get something like 0.2676. Definitely feel free to check my math there. But if 73.24% is below, that means that 26.76 is above. And once again, if you add the area in this shaded area and this white area, it should add to 1, always. Anytime it doesn't, something's gone sideways. So this is a handy, although very technical looking probability. So setup, if you have your z-score, you can just skip straight to the table. That's pretty much what that's saying. And the table, the z table that we use, gives us the area underneath the value. If you have a normal distribution and you don't have a z-score yet, this basically says, well, calculate your z-score and find the probability less than that z-score. If you want an area above, you have to do that 1 minus. So anytime you want the right area, you're going to have to do a 1 minus bit once you have a probability. Anytime you want the left area, the left-hand area is the default on our z-tables. The right-hand area is not. And then this one is really handy, is if you want to find the probability that x is between two values, you calculate 2 z-scores and 2 probabilities. So you'll end up taking the bigger probability minus the smaller probability. And the area left is the area in between. And I'll talk about it a little bit in an example. So we're back to the bridges. I warned y'all, we really like these bridges. So we have a bridge, we have vehicles driving on this bridge that are normally distributed speeds with a mean of 58 miles per hour and a standard deviation of 10. So it just means that it's centered at 58, and then each of these tick marks is 10 away. So suppose a randomly selected vehicle, they're going 40 miles per hour, so they're somewhere over here. We want to know how many standard deviations from the mean it is. So just looking at it, here's the mean, here's 1 less, and here's 2 less. It's somewhere between -1 and -2 because it's less than. I don't know exactly where it is, but we can figure this out. So what it's asking essentially is what our z-score is. So here it's x minus mu over sigma. So x is going to be that 40 miles per hour. Mu is just the mean of the whole thing over sigma is 10. So I'm going to get -18 over 10. That's going to come out to -1.8. So what this means is a car going 40 miles per hour is 1.8 standard deviations below average. That's what that's saying. Then I can go ahead and ask this follow-up, well, what is the probability of selecting a vehicle going less than 40 miles per hour? So I can say, okay, well, what is the probability I randomly select a vehicle and it's going under 40 miles per hour? What's really cool is we calculated the z-score already. It's the same as the probability that z is less than negative 1.8. I'm going to throw in a 0 there. It'll make it easier. So we want this area here. And I will go to the next slide because I actually have a table on there. So probability x is less than 40 is the same as probability z is less than negative 1.80. I'm going to split this into negative 1.8 and 0, 0. So here's my row, here's my column, line it up. So if I have negative 1.8, this shaded area is 0.0359. And right now, we wanted the area less than, right? We want to know the probability of randomly selecting a vehicle and it being under 40 miles per hour. So this is what we wanted. So we can just say, okay, that's 0.0359. So that happens about 3.59% of the time you randomly select a car and it's going under 40 miles per hour on this bridge. Which honestly doesn't seem like that happens that often. It seems like really, really high speeds on this bridge. So as a follow-up here, so suppose I have a same bridge, but now I want to find out what is the probability of selecting a vehicle that's going more than 140 miles per hour. So here, if this was going 0.0359, and I want this whole shaded area, I'm going to use that complement rule. I'm going to say, oh, well, this shaded area is 1 minus 0.0359. So probability that x is going faster than 40, that's just going to be 1 minus the probability it's going slower than it. So 1 minus 0.0359. It's going to come out something like 0.9641. Please definitely check the math. I'm doing this in my head here. I've also done a lot of adding and subtracting from 1, so don't feel bad if you're not in the same place where that particular mental math is really speedy for you. So if 3.59% are going slower than 40 miles per hour, that means that 96.41% are going faster. So now, the trickiest follow-up one we've had so far was the probability of selecting a vehicle going between 40 and 65 miles per hour. So I'm going to go ahead and draw here. So 40 miles per hour and 65 miles per hour. So just to illustrate here, so for me, if I want this here, so probability that it's between 40 and 65, oops, I need an x here, because x is the speed. I can write this, or rewrite this as probability that x is less than 65 miles per hour, minus the probability that x is less than 40. So, translation here, so this whole area here, this is the probability x is less than 65. this tail end probability here. This is the probability that x is less than 40. So in essence, I want to take this whole thing, this whole shaded area, and just cut off the part I don't want. And then what's left is just the middle part I do want. That's what I'm doing. So for each of these, we figured out this probability in that earlier problem. We are going to have to get a z-score for this. So if we didn't calculate a z-score for the second part, we'd have to calculate a z-score for each part here. So I'm going to go ahead and do this. So probability x is less than 65. I am going to get a z-score for this. So z is less than, and I'm just going to write the equation, then fill in. So x is what I'm interested in, 65. So 65 minus 58 is the average, over 10 is the standard deviation. 10 is such a nice friendly one. I'm going to get something like 7 on top, 7 over 10, so positive 0.7. I'm going to throw in a 0 because it's a z-score. So I want to figure out, that's the same as the probability that z is less than positive 0.7. So I'll use a z-table for that. So probability that, so this is still that sort of side quest, that z, well, x is less than 65 is the same as probability that z is less than positive 0.70. I'm going to break this up. So positive 0.7 and looks like I have a 0 in my hundredths place. That's what goes here. So 0.700. Okay. So 0.7580. This is an excellent place to stop and go, have I answered the question? No, not quite yet, right? We went off on a side quest. So now, let me see, does this next, nope, not quite. Our next part, so finish, probability that x is between 40 and that x is less than 65. Okay, so now to finish, that probability that x is less than 65 minus the probability x is less than 40, that's going to be equal to this thing that we just calculated, so 0.7580 minus, I'm pulling this from that other problem we just did. So that was 0.0359 because we did that in that previous part. So throw this into a calculator. I'm not nearly as good with subtraction as adding to 1 here. I would recommend using a calculator anyway. Something like 0.7221. So this would be my answer to this question. So that being, if I were to randomly select a car driving on this bridge, 72.21% of the time, the car is going to be going between 40 and 65 miles per hour. And then we have a last short topic in here. So using percentiles. So in general, we're specifically going to focus percentiles for a normal distribution. So we're going to go ahead, x, and then it has a subscript. So p over 100 represents the pth percentile. So what that means is x, 5 over 100 is the 5th percentile. You could also write x 0.05 is the 5th percentile. The idea is it's the value that 5% of the others fall below. So if I took an exam and I am in the 13th percentile, it means that my score is above 13% of the other scores. That's what it comes down to. So if I want to calculate a certain percentile, we'll need the z value associated with it, and we'll go through finding that. We'll multiply it by the standard deviation of the population. So multiply first, then add the mean, and that will give us the value. So if I wanted to know, okay, well, what score on this exam is associated with the 20th percentile, I could find the z from the table, and then I would have this information about the problem, and I could find what score on that exam had 18% below it. That's what I'd be calculating. So it's always going to be talking about area to the left. So the 5th percentile is 5% to the left. The 95th percentile is 95% to the left. So here we have bridges, and we might want to know, okay, what speed represents the 5th percentile here. So what we're asking here, it's somewhere in between here, not sure exactly where. We want to know what speed has 5% below it. That's what we're asking. So we want to know what this speed is. Somewhere between 30 and 48, but that's really not a lot of information. So we're going to, our first step, we need to find the z value associated. So we're actually going to work backwards from what we were doing before. So here, now I'm focusing in here. I want to look in here, and I want to look for, so 5th percentile, I want to get as close to 0.05, well, 00, as possible. I want to just get as close as I can. So if I look here, 0.0274, it's not as close as I can get. 0.04 is closer. If I look here, it actually looks like it's going to be between these two, right? 0.05 is somewhere between 0.0505 and 0.0495. I personally, these are equally close too. So honestly, I like to pick the one that is at least 5%. If I want the 5th percentile, I want at least 5% below it. Honestly, as long as you pick between one of these two, we don't care which one you pick too often. So now you have to work backwards. So now that you found as close to 0.05 as you can get, you're going to work backwards to get a z. So now my z is going to be negative 1.64. So now we work backwards. This is the z that I'm going to use. Mu is going to be the same. So mu is 58 miles per hour. And sigma is going to be the same, 10 miles per hour. Let's see. Oops. So z is equal to negative 1.64, at least using the table. So now we're going to find, okay, well, x for the 5th percentile, so 0.05, or 5 over 100, is equal to, I'm going to have z times sigma plus mu. So I have everything I need to plug in here. So is equal to negative 1.64 times 10. So nice. I love multiplying by 10. Plus 58. So I'm going to get something like negative 16.4 plus 58. And right off the bat, this tells me, hey, this is going to be lower than 58, which it should be, right? If I'm looking for the 5th percentile, right? Because the 50th percentile is at the mean, right? Because it's perfectly symmetric, so that means half is lower than it. So I definitely know it has to be somewhere over here. Do some math here. Something like 41.6 miles per hour. So I am asking about speed, so I'm going to throw my unit in here because there are units here. So what this means is a car going 41.6 miles per hour, only 5% of cars are going slower than that speed on this bridge. So now flip side, we're going to do, we want to know the 95th percentile. So we want to know, well, okay. So this question is really, really similar. So what speed do only 5% of vehicles exceed? So we want to know 5% above. So I'm just drawing a line here, I'm guessing, roughly. And I want to know 5% or 0.05 right here. Well, I don't want to use, per se, the 5th percentile. If I have 5% above, this means I have 95% below. So I want the 95th percentile. So be careful about wording. Definitely pay attention. Do you want 5% like lower than or 5% higher than? It definitely is going to be important. So 5% higher than means you really want to find what the 95th percentile is. So you need to find your z. That's still our first step. And it's actually going to be really, really, so if we want the 95th percentile, we want as close to 0.95 as we can get. So you'll notice that here 0.95 is above 50, so I'm going to be using the positive z-table. If the percentile you're looking for is below 50%, you'll use the negative z-table. So looking here, obviously this is very, very cropped. This is 91.92%, 93, 94. Oh, look. This is cropped beautifully, right? So I'm going to pick between these two. Usually you would just pick whichever's closest, but it's exactly halfway in between. I'm going to just lean this way. It's not going to matter if you pick 1.64 versus 1.65, not really. So working backwards, z is equal to 1.65. Note you could use 1.64. Note that it's totally the opposite. So in reality, I actually know that, and we're not going to do it here, but I know it's actually 1.645. It's actually exactly in between. So if you want 5% here, this is positive 1.645. If you want 5% here, this is negative 1.645. Because the normal table is exactly symmetric. That's why. So we're going to grab this here and go back to the other page. So I'm going to use z is equal to 1.65. You're welcome to use 1.64 or 1.645, but whichever. I know it's 1.645 from other things, including software. I don't expect you to calculate that exactly. So I now know, so x is, for the 95th percentile, I'm going to need z times sigma plus mu. So we have, this is sigma, and we have mu here. So it's equal to 1.65 times 10, multiplied by 10, so nice, plus 58. So you're going to get 16.5 plus 58. So it's going to be above average. Do some math. I get something like 74.5 miles per hour. Because remember, x are vehicle speeds. Right? So if I'm solving for a vehicle speed, it should be in whatever unit vehicle speeds are in, miles per hour here. So translation, what this means is only 5% of cars are going above 74.5%. So what this means here, just translation, is only 5% of cars are going faster than 74.5 miles per hour. It means that 95% are going slower than that 74.5 miles per hour. I believe, oops, let me just hit my microphone. I believe that's going to be it for our, nope, there's one more. So here we have a particular bridge, same information here, and we want to know the median speed. So median is 50th percentile. We want to know where exactly half are above and half are below. So for me, I usually jump straight to, oh, it's the mean. It's 58 miles per hour. And that's correct. But we're going to go through some of that logic here. Right? So we want the 50th percentile here. So here, if I want to do it the other way, so find z, go in here, I want to find so for 50th percentile, oops, my handwriting's getting worse. You want to get as close to 0.5000 as you can get. So I'm going to look in here and try and find 0.5000. Ta-da, it's right here. So it's exactly right there. So if I work backwards, my z score here is 0. So I can go ahead, use that here, z is equal to 0. And then I can say, okay, well, the 50th percentile, that's going to be equal to z times sigma plus mu. So I love multiplying by 0. 0 times anything just makes things go away. So 0 times 10 plus 58. This is going to be 0 plus 58 is equal to 58 miles per hour. So there you go. This right here was the long version, but we wanted to explain you will get in the same place. The median, remember, if you have symmetry, the median and the mean are equal to each other if it's exactly symmetric. And the normal distribution is. So really, really, really handy there. So I believe that one is it. Definitely check out the your turn slides. When it comes to figuring out reading the z-table, the best thing for that by far is practice. So I look forward to hearing from y'all. Hopefully I'll add to the discussion this week.